The following diagram represents what is called the difference quotient, a very important concept because it sets us up with a secant between 2 points on a function f of x. Now in this diagram, we don't have to know what the actual formula for f of x is. And that's because this concept will apply to any function. The idea is we'll pick 2 points, the beginning and the end of our secant. And we want to calculate the slope of that secant, but we want to do it generally. So there's no numbers given. What we do is we pick a point x on the x-axis, and that's going to be the start of our interval. Then we have to go some arbitrary distance away from x, which is called h, and h is the length of our interval. In order to get the heights off the ground or x-axis for these points, we want to do the function on the inputs of x and x plus h respectively. From this, we're able to give a formula for a rise and a run. The rise will be f of x plus h minus f of x, so the difference in elevations of these 2 points. And then the run will simply be that distance h. Now h could be anything. So let's start off just by writing a difference quotient generally for some different functions. So here's a function, f of x equals x plus 3. It's a good one to start with because it's actually just a straight line. And I'll draw a graph of it. Now imagine I was to pick an arbitrary point on the x-axis, which I'll call x, and I'll get this point here, which has a height of f of x. Now we're going to go some arbitrary distance away from x, which will be h. And we want to trace that up so that we get a point on the function itself. And let's just trace that over here. And now here we have f of x plus h. All right, what we want to do is we want to create a triangle out of this. It has a width of h, and the height of it will actually be given by f of x plus h minus f of x. So that's all we're doing, is we're just trying to calculate a slope for that function there. Now, you know from your experience with linear equations that the slope should just come out to be 1. According to the formula of mx plus b, the m would be 1 here. So let's see if the difference quotient for this function actually does yield 1. Okay, so our goal here is to plug into the difference quotient, which says f of x plus h minus f of x over h. But we don't want to just leave it as a letter f. We want to use the actual function that was given. They said f of x equals x plus 3. So maybe before we even start to plug in here, let's just on this side, just remind ourselves that if we have f of x equal to x plus 3, then what would be f of x plus h? Just so that we have that written down on the side so that we can substitute it in. Well, if you recall from section on functions, one way to plug into a function like this is to use open parentheses. Because if I were to have f of apple, for example, then what would it be? Apple plus 3, right? Whatever is in those parentheses, that's what has to go in place of x. So what actually goes here then, in this case? X plus h goes there. Okay, so it could be helpful at this time to take the f of x plus h out and put parentheses in its place. And do the same thing for f of x. Now, what will go in the place of f of x plus h? Now we want to refer back to what we had said above. F of x plus h is x plus h plus 3. And in the place of f of x, we just need x plus 3. The reason why the parentheses are helpful here is you got to make sure that the entire f of x gets subtracted. And if those parentheses weren't there, that would mean the negative only applied to the x, but we need it to apply to the whole thing. So the parentheses there are important. Now what we want to do is we want to just simplify and see what we get. So the x plus h plus 3 can stay. I'm going to distribute that negative. I like to do one thing at a time. And often with these, we can cancel some things. So it looks like the x's will cancel. And even the 3's will cancel too. So what does that give us? H over h, which is 1. It shouldn't be a surprise because that actually is the slope of x plus 3. Now it seems like a difficult way to find it, but the reason why this one we're able to find the slope is because it's linear. The slope is the same everywhere for a linear function. But as we'll see with some functions, they're going to have changing slopes. Slopes that can't have just a single number. They're going to have formulas instead. So at this time, go ahead and try B, and then I'll give my answer. All right, for B, we have f of x equals 2x plus 5. So for f of x plus h, we're going to have 2x plus h plus 5. All right, now let's write the difference quotient. Put parentheses in the place of f of x plus h. And divide by h. Then let's go ahead and put their formulas in here. All right. Now let's try to simplify. I'm going to distribute the 2 to both of these, and I'm going to distribute that negative as well. So we'll get 2x plus 2h plus 5 minus 2x minus 5. And that's over h. All right, so some things cancel. 2x and negative 2x, 5 and negative 5. And what are we left with? 2h over h, which is, of course, 2. Does it make sense that the difference quotient here yielded 2 for this function? The formula was 2x plus 5, which is a linear function, and it has a slope of 2. So when we did the difference quotient, we found a slope of 2 as well. Notice that it is independent of our choice of x and our choice of h. Our final result here doesn't have an x or an h in it, which means it doesn't matter what x and h are. The slope of that linear function is just always going to be 2. So now what we want to do is we want to look at one that's more complex. And that is C, which is f of x equals x squared. I'll move way over here to do that one. Okay, so C. For C, we want f of x to equal x squared, and we want to calculate the difference quotient. All right, so let's go ahead and find out what f of x plus h is, just for our own reference. If f of x is x squared, then f of x plus h is x plus h squared. Now we want to write the difference quotient out. All right, we'll substitute in. And we're going to have to expand this in order to simplify. So we'll do x plus h times itself. Which is going to be x squared plus 2xh plus h squared minus x squared over h. We can cancel the x squareds. We'll be left with 2xh plus h squared over h. When we have two terms being divided by a single denominator, we can break them up into two fractions. That's a useful technique here for simplifying. And let's see, the h's will cancel. We'll get 2x plus h. And that's our final answer. What this shows is that the parabola is fundamentally different from a linear function. Linear function just gave us one number for the difference quotient, which was the slope of the line. Here, the results are much more complicated, and it shows that our function's slope would depend on the x where you start your secant line, and also the h, the width of your interval. Both of those things will play a part in the slope that you get for your secant line.